Have you ever noticed how certain elements behave in a similar way, even though they're placed far apart on the periodic table? Like how sodium and potassium react explosively with water, or how fluorine and chlorine love to gain an electron. That's because these elements belong to the same group and share what we call periodic properties. The modern periodic table is built on a powerful principle. Properties of elements are periodic functions of their atomic numbers. That means when elements are arranged by increasing atomic number, their chemical and physical properties repeat at regular intervals. This periodicity is due to repeating patterns in electronic configurations, especially in the valence shell, and it makes the periodic table not just a list of elements but a map of chemical behavior. So, what exactly are periodic properties? They are atomic and chemical traits that show regular trends as we move across a period or down a group. Some key periodic properties include atomic radius, the size of the atom, ionization potential, the energy needed to remove an electron, electron affinity, the energy released when an electron is gained, electronegativity, how strongly an atom pulls bonding electrons, and metallic or non-metallic character. Other traits like density, melting point, and the acid-base nature of oxides also follow periodic trends. These patterns help us predict the behavior of unknown elements, design reactions, and even build materials in industries from electronics to pharmaceuticals. Let's begin with atomic radius, or the size of an atom. Definition: it's the distance from the nucleus to the outermost shell of an atom. Now here's how it changes. Across a period from left to right, the atomic radius decreases. Why? Because the number of protons increases, pulling electrons closer to the nucleus without adding a new shell. Down a group, atomic radius increases. That's because each step down adds a new electron shell, increasing the atom's size, even though the nuclear charge also increases. Example: in period 2, lithium has a larger radius than fluorine. In group 1, lithium is much smaller than cesium. Now, let's talk about ionization potential, often abbreviated as IP definition. It is the amount of energy required to remove one electron from the outermost shell of an isolated gaseous atom. Let's see how this property behaves. Across a period, ionization potential increases because atomic size decreases and electrons are held more tightly. Down a group, it decreases as outer electrons are farther from the nucleus and more easily removed. Equation: M plus energy gives M plus plus E minus. This property helps explain why metals like sodium lose electrons easily, while nonmetals like nitrogen hold onto them tightly. Moving on to electron affinity, or EA definition, electron affinity is the energy released when a neutral gaseous atom accepts an electron to form an anion. Across a period, electron affinity generally increases, especially among nonmetals, because they want to complete their octet. Down a group, electron affinity decreases because the added electron enters a shell farther from the nucleus, so less energy is released. Equation: X plus E minus gives X minus plus energy. Fluorine, for example, releases a lot of energy when it gains an electron. It has one of the highest electron affinities. Noble gases, on the other hand, have almost zero electron affinity because they're already stable. Next, let's explore two very important properties: electronegativity and metallic character. Electronegativity is the ability of an atom to attract shared electrons in a covalent bond. Trend: it increases across a period as atoms become smaller and pull electrons more strongly. It decreases down a group as atoms become larger and pull electrons more weakly. Example: in hydrogen chloride, or HCl, chlorine has a higher electronegativity and pulls electrons toward itself. Metallic character is the tendency of an atom to lose electrons and behave like a metal. It follows the opposite trend, increases down a group, decreases across a period. That's why sodium is metallic, while chlorine is non-metallic, even though they're in the same period. Let's quickly wrap up the periodic trends. Periodic properties show regular patterns because of the changing valence electron configuration as we move across periods or down groups. Across a period, the atomic radius decreases, while ionization energy and electronegativity increase due to stronger nuclear attraction. Down a group, the atomic radius increases, and both ionization energy and electronegativity decrease as added shells reduce nuclear pull. Metallic character falls across a period but rises down a group, helping us understand the reactive behavior of elements. These predictable trends are key to understanding the structure and chemistry of the periodic table.